can you see the question now? Can you see the question and the screen that I've just written on in red? Can you see those two?
I can only see the diagram and the question is covered.
Okay, okay, let's see what's happening there. Thank you for highlighting that. How is that now?
Yeah, I can see the question now.
Okay. All right, thank you. So how do we get the energy stored in C3? How do we get the energy stored in capacitor C3 in this setup? The values of the other capacitors are given. What's our starting point? Where do we start from? Yes,
Okay, so let me try.
good.
Because for this circuit we have both parallel and series connection,
Very good, yeah.
and C3 is connected in parallel with C2, but also you can view it as a series connection if you connect if you add C1 and C3 with the other capacitors. So the voltage will be divided between C1, C4, and C3 plus C2.
Okay, very good.
And the voltage, yeah, and that voltage divided, you find that voltage and use that, and the voltage between C2 and C3 will be equal. That voltage, you're going to use it to calculate the energy with equation 1/2 C V squared.
Perfect, wonderful. Thank you for that detailed description. So, which means for us to find that voltage, already we know our supply voltage is 45, and we know our energy is half of what? CV squared, right? Like that. So, in other words, since we have the value for C3, we need to find at least that voltage across C3. So now, to find this voltage, we simply need to first evaluate the total, what do you call this? At least the total capacitance in this system, so that we'll know how the voltage is divided in each case. So for our total capacitance, we know that the two capacitors that you have identified as C2 and C3 will have will be C2 and C3 being parallel capacitors. So as such, their total capacitance or their equivalence capacitance, C equivalent, is equal to capacitor 2 plus capacitor 3. That's for parallel capacitors. So their capacitance there will be C2 is 10, C3 is 14. So this is 10 microfarads plus 14 microfarads. And that gives us a total of 24 microfarads at that parallel part of the circuit. So this equivalent capacitance is like a single 24 microfarad capacitor at that point where we have a parallel connection of C2 and C3. Then from there, we have C1 and C4. So with C1, C4, and the equivalent capacitance, we can then say the total capacitance will be the inverse of 1 over C1 plus 1 over C, what we called the equivalent, what we have calculated, plus 1 over C4. Everything inverted. So you would say 1 over CT equals to 1 over C1 plus 1 over C2 plus 1 over C3 as you go on if you have your series capacitors connected like that. So this becomes 1 over C1 being 20 plus 1 over 24, which we have already calculated. All these are microfarads, plus 1 over 30, 1 over 30 microfarads. And after adding that, we invert that sum. So that should give us the total capacitance of this system. What would we get? What is this total capacitance? What is this total capacitance?
I got 8.
8, very good. So we have 8 microfarads as the total capacitance. And with this total capacitance, we therefore can, what we can then do there is to find the total charge within this setup. We can find the total charge within this setup. How do we find that total charge?
By multiplying the capacitance and the voltage.
So if we multiply Q, the total charge is CT times voltage, the total voltage which we already have. So we have 8 microfarads multiplied by 45. We find that we have a total charge of 90 by 4, 360 microcoulombs. Do we agree? So the total charge in this system is 360 microcoulombs. Do we follow so far? Or have I lost you?
Yeah, I'm still following, sir.
Still following, okay. So if we have this as our total charge in the system, why is this important? This actually helps us. Unfortunately, I didn't draw the circuit myself, but anyway, it's a very simple one. That part, this parallel part connected. So forgive me, I'm just trying to make a quick sketch there. So we've got our voltage supply, C1, C2, C3, and C4. Now, what does this 360 microcoulombs mean? It is the total charge contained in the system. Remember, in this part of the circuit, what information or what should we remember for capacitors connected in series? For capacitors connected in series, what is the important property that we should always remember? Or maybe let me leave it there. Okay, good. Okay, come in. Yes.
A charge in series.
Mm-hmm.
And in a parallel connection, the charge is divided.
Okay, you said in series, what happens to the charge in series?
I think in series the charge is going to stay the same.
Very good, wonderful.
It's not divided in a second.
Well said, yes. So if we have a series connection, so remember our equivalent capacitance, we have considered this parallel part as what? As an equivalent capacitance, which is represented by that. So this equivalent capacitance is now in series with C1 and it becomes C equivalent, and we have C4. So now this is a series connection, and in this series connection, the Q1 is equal to Q equivalent, and is equal to Q4, and is equal to Q, the total charge, Q total, whether did you find it as Q total there? Yes, Q total. You get the sense? Why? Because the current that would flow in leaving a charge at C1, it leaves the same charge at the equivalent capacitance, it leaves the same charge at C4. So ideally, if you have one capacitor and we connect another capacitor across it, if the charge was Q here, so remember when we are charging, we put positive, we deposit positive charges there, negative charges there. When we connect this capacitor, the second one, C2, we deposit, ideally what then happens is we induce a charge, a positive charge, ideally here, positive charge, and also have a negative charge there. So at the end of the day, the charge that is between these two outside plates is still Q, if it was initially Q on that one plate. So we still have the same Q in the system. So that's where you don't do Q1 plus Q2, is still the same Q across both of them. Right, so that's the idea. It's you don't need to think hard or try to think much about the addition and everything, but generally look at it as this in this sense, to say this is your left plate, the plate that's positive, that's your plate number 1, this side. Then your plate number 2, the negative plate, that side. So the capacitor, this is now just like one capacitor with still the same charges on either side. This part is only isolated. So this part is isolated, and it just redistributes the charge. So there's just distribution of charges there, but it doesn't affect the overall charge of the system in a way. So as you have already told us, our Q, the charge on C1 is equal to the total charge. The charge on C4 is equal to the total charge, and the charge on the equivalent capacitance, which is the two parallel capacitors, will also be equal to the total charge. So now that we have found this total charge, it means this is the same total charge that is on these two capacitors. So because we found this total capacitance after adding the parallel capacitors, the total capacitance there is 24 of that equivalent capacitance. Then it means we can now find the voltage across this total capacitance. What is our formula for voltage? What is our formula for voltage? Did I lose you somewhere? Somehow, did I lose you, or we're still together?
Actually, I think I'm lost.
Okay, no problem, no worries. So let's do this. Remember, maybe I shouldn't have explained a lot anyway about this whole thing, but it's okay. So what we have found is total capacitance, which is 360. What happens, the reason why I asked about this, it is very important. So the reason why I wanted to emphasize on this, if we leave it unaddressed, it will always be confusion. Like even like when you look at the questions that will follow when we charge capacitors, isolate them and connect them to other capacitors, whether in series or in parallel, it is important to know this. So our starting point, we know that when we connect systems in parallel, what remains the same, excuse me, is the voltage. The voltage is the same for systems in parallel. So we expect the voltage across C2 and C3 to be the same. That one is not a problem. And we know why it should be the same, right? Now, we're talking about capacitors in series. When capacitors are connected in series, you gave me this, you told me that the charge remains the same. I was just trying to explain why that charge remains the same so that you don't forget. So that's why I came to this to say, if initially we have a single charge, a single capacitor C1 with a charge Q, right? Then the current that deposits that charge Q will be the same current. If we connect a second capacitor, it will be the same current that will pass through C2 and also deposit another similar charge Q or same charge Q. So when the same charge Q is deposited there, the total charge of that system of capacitors of the equivalent capacitance is still Q, because we are not adding the charges on the two capacitors. It's not Q1 plus Q2. The total charge, the charge on C1 and the charge on C2, the total charge is still Q, deposited by the same current. So what I was explaining further was to say, think of it as bringing in this new capacitor is like just taking out, let me see if I can do this. It's like, think of it as what would happen when, is this, that's not an eraser. When we remove this part and we still have that capacitor there, we still have that capacitor like that. It means the charge that accumulates on that side of the plate and this side of the plate is still Q. So this side that was the inner parts of the plates, they are just isolated and connected together. And at the end of the day, they don't change the total charge that is within the system. So the charge is then said to be, the charge on C1 will be Q1, like I said here. The charge on C2 will be Q2, and the total charge between them is the same as what is on Q1 and what is on Q2. So they have the same charge, and that charge is the total charge of the equivalent capacitance. So the reason why we had to do that is to try and find at the end of the day how much charge is on this combination of capacitors. And we say that total charge on that combination of capacitors is still 360 microcoulombs, same as the total charge of the whole system, because now we have a series connection. This is now a series connection through across the set of capacitors from C1 through C equivalent through C4 and back to the circuit. So while it's in series, if our equivalent capacitance is 24, our total capacitance or our total charge in that capacitor is 360, then the voltage V is equal to Q, Q total, which is the same as the equivalent, over the C equivalent. So this charge 360 microcoulombs over 24 microfarads will give us a value. And what is that value? What is that value for the voltage?
You are cutting, sir. I can't hear you.
Oh, I'm breaking. So I was asking, saying if we say the total charge on the equivalent capacitance is the same as the charge in the total capacitance, or in the total equivalent capacitance of the whole circuit, then this total charge being 360, it means that that's the same charge that is on the parallel capacitors. So we say this same value, 360 microcoulombs over 24 microfarads, gives us a certain voltage. And what is that voltage? What is that, the value of that voltage?
It's 15.
It's 15.
15.
15 volts. So now, because we are on a parallel circuit, it means the voltage across C3 is 15 volts. So we're 15 volts across C3, we're 15 volts across C2, because we know that for parallel connections, the voltage across each unit or each line will be the same. So now we have already found the voltage which will be across C3. We know the value for C3, which is given. Sorry, this is supposed to be 3. The value for C3 is 14. So if we know the value for C3 and we know the voltage across C3, what is the energy stored by capacitor C3? In that equation. So we said energy stored by C3 is equal to half C3 V3 squared. C3 is 14 farads, sorry, multiplied by 15 volts all squared. And what will be that energy?
1575 joules.
Is there no, remember it's microcoulombs. Did you put the micro there?
Oh yeah.
So it's times 10 to the minus 6, eh?
Yeah, times 10 to the minus 6
So
for the capacity.
So that will be 1.58 millijoules. 1.58 millijoules. Thank you for that calculation. Figures were right. Don't forget the prefixes there, the micro, the milli. You should include them in your calculation. So with that, I think we have, let's see what answers are there. So 1.58 millijoules, there we are. Okay, like that. So that's how we get to that conclusion. That's how we get to that conclusion. So what is important there is to know the rules, or at least the governing principles behind different connections. Your capacitors in series, you should know the charge in each of them is the same, and that charge is the same as the total charge in all of them. In as much as it sounds confusing, but that it is, that's the way it is. Okay, shall we proceed? Okay, so this one has got a diagram. The question reads: two parallel conducting plates form a capacitor. It is isolated and charged, and a charge Q is placed on it. A metal cylinder of half the plate separation is then inserted between the plates. How many of the quantities C, delta V, Q, E, and U would change? So there is a metal cylinder introduced between the plates as shown in the diagram by that. And the thickness of that metal cylinder is D. So that's the part that you would want to see there. It's just D. Then the question says, on introduction of this metal cylinder, which is whose thickness is half the plate separation, or whose length is half the plate separation, how many of the quantities between C, delta V, Q, E, and U would change? C, what is C? What is delta V? What is Q? What is E and U? I think that is also equally important. What are those quantities? What are those quantities?
We have the capacitance, the voltage, the charge, the electric field, and the energy.
Very good. So we have the capacitance, C, the voltage across the plates, across the capacitor, delta V, the charge, Q, and the electric field, which is the potential difference per unit length. So it's the electric field strength, and U, the energy stored by the capacitor. So we want to know whether it changes or not. So would use that and that for yes or no. Does the capacitance change Will the capacitance change? Will the capacitance change? What do you say about capacitance? Change or no change? Change or no change? On introduction of
As
yes. Yeah, I'm listening.
actually, sir, I don't think it will change. It will stay the same.
You think it will stay the same? Do you have a different
Yes.
formula for capacitance, different from the one that we have been using here? Have you come across a different formula to which one? Did I just
No,
erase?
sir.
Yeah,
No, sir.
one that considers the dielectric. C, we have said C is
Or
charge.
CK.
Okay, good. Or C equals to A E naught K, yes, over.
I forgot the formula.
All right, let's do like this in case you forget again. The capacitance, considering parallel plate, is it directly proportional to area or inversely proportional to area?
The what?
The capacitance itself, the ability to store charge, how does it change with surface area? Like if you've got bigger plates and smaller plates, which one stores more?
Yeah, the bigger your plate, the more you can store energy.
Wonderful.
So
Yes.
yeah, the capacitance is directly proportional to the area.
Right. What about to the distance of separation between plates? The distance of separation between plates. Closer plates, further away plates.
With when plates are further, yeah, I think the capacitance can be weaker.
Yes, so it's inversely
I'm
proportional.
not sure.
Yeah, right. It's inversely proportional to the distance of separation, right? Then it will also be affected by the dielectric constant, which is in this case given by our introduction of the K. Because this E naught is basically the free space permittivity, but then we talk of the dielectric constant, which is given or introduced by K. So the moment we introduce the dielectric constant, we also increase the capacitance. So this is another formula for your capacitance, to think of it in terms of the physical parameters or its physical makeup.
I thought only insulators can be dielectrics. I don't know even conductors.
Yeah, by saying dielectric, we're just saying the material. We're just looking at the nature of the material that we put in there. So the conductor can also have its kind of dielectric, but insulators, in this case, they make the best dielectric for us to store more charge, because we don't want to have any charge leakage. So a conductor would not be ideal to put in there. But anyway, it does affect the capacitance at the end of the day if we are to put it in there. You get the sense?
Okay.
All right, but anyway, still back to the question. Besides, if we introduce this material with a different dielectric constant, does it affect the capacitance? Now back to the table. Is it going to affect the capacitance?
Yes, it's going to affect the capacitance.
Yes, it's going to affect the capacitance because it introduces that factor, the K. So the capacitance will change. We can say it changes, will tick. What about the voltage across the capacitor, across the plates? The voltage across the plates. Change or no change?
I'm not sure because the voltage is supplied by the battery. and it can be constant. But if you look at the formula, in this case, our dielectric is a metal, and metal is is a really good conductor of charges. It can increase the capacitance there. So but the capacitance is also inversely proportional to the voltage. So I'm confused.
Okay. So okay, one thing for sure is what you like you said the dielectrics you know them as insulators. You want insulators because they are the ones that increase capacitance. They increase the ability to store charge rather than having a conductor which will cause charge leakage. A conductor will ideally cause charge leakage. So introducing this conductor might actually result in a what in a decrease in the capacitance of this system. But anyway, besides, we are just looking at generally whether it increases or decreases. We are worried about the change. So the thing to do with voltage now, to think of the voltage. This for this question. Sorry, let me. So for this part of the question, remember, these are conducting plates that form the capacitor, and they are isolated, meaning they are removed from a source which actually introduces the charge into the system. So they are charged using a battery, like you said, you can use a battery, you can use your DC source, you charge the capacitor. But after that, you isolate them or disconnect them from the battery. So after doing that, the charge remains on the capacitor. So now that we have charged this system and isolated, we no longer have any further supply of charge. We now are dealing with the charge that has already been deposited onto this capacitor and isolated. Now introducing this system, it simply means if you look at the first equation, C equals to Q over V, right? We have already seen that the charge in this system is already deposited onto the capacitor. So once it's deposited like that, it won't change. It remains the same. We don't have any means by which the charge will be lost or any means by which the charge will be gained because the battery has been removed. So charge remains constant. But because this one changes, something else has to change. What then changes to counter the change in the capacitance?
The voltage.
The voltage does change. So the voltage
Yes.
will also change, yes.
Yes.
So you are actually being guided by the fact that we have isolated this system. So this part is actually important to have isolated the capacitor and the charge Q that is placed on it so that the charge remains the same. So once this charge remains the same, it now controls or determines this behavior whereby because we introduce a different dielectric, capacitance will change. If capacitance decreases to half, the voltage doubles or increases by 2, by a factor of 2. It doubles. So if the capacitor is if the dielectric comes in such as to double the capacitance, the voltage should decrease to half. So that's how this isolation really, what it really means and how it really affects the whole system. So which means according to the table, we also tick this one changes. What about Q? What about Q? What about Q?
Yeah. With
Yes, yeah, try.
I'm still gonna use that argument because they've inserted a metal. If that metal is charged or has a charge, it has to change.
So the metal is just coming in as a dielectric, remember. So the charge that we have in this, basically in this system, like let's say the metal is just being brought into this system neutrally charged, with just generally as a neutral dielectric. So it is just a dielectric, it doesn't introduce charge into the system. But does the charge that we have deposited on the capacitor change? So take note of what I...
No, they
Yes.
okay. Oh yes, I understand. If that metal is only acts as a dielectric, then that charge deposited on the capacitance will not change.
Will not change. Yes, that's the basis upon which we kept it constant here, and so that it is the voltage that should change along with the capacitance. So the charge should not change. Charge should not change. Then what about the energy? What about the energy?
The energy, I think the energy will, yeah, the energy will stay the same also.
How come? How is that? Remember our formula for energy. What are your formulas for energy in terms of C, Q, and V? Energy is equal to
Half CV squared
half CV squared.
and
Or
that I forgot that one.
okay, half CV squared or half QV, right? Or half, if we substitute for V there with a Q over C, half Q squared over C. Like that. So these are the different variations of our formula. So now, because we have said Q remains the same, but V is changing here, will E not change according to this?
Okay, so but yeah, it will change, but here are my reasons now.
Okay.
First, I just realized because I thought because Q will stay the same and C and V will be the ones changing. If this one increase, this one will decrease. So when I look at this formula, I have CV squared. I thought CV will balance each other out, but I just realized the voltage is squared.
Is squared. Good. Yes, 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 yes,
Yeah.
yes. So that V that
Yes,
remains there will actually remain with the change.
yes,
Yes, perfect. So ultimately our E should change, right?
yes, it
Our
will
energy
change.
should change. Okay. So sorry. I'm looking at energy. Electric field will be something else. Okay. So this one we've done. What about E, the electric field? Now I was saying E is energy. U is the energy CV squared. What about the electric field? E. We say this is delta V over D. Delta V over D. What will happen to that one?
And with this one, we already know that the voltage will change, but what about the distance? Is the distance the distance between the plates? It
Constant.
doesn't matter if where the dielectric is
Yes.
relative the distance of the dielectric relative to the plates.
So that distance is basically only the distance between plates. So whatever the dielectric, whether the dielectric is also equal to 3/4 of D or half of D, its properties or whatever its dimensions are, they only affect the amount of the value of K that goes into that system. So it doesn't affect D, is only the distance between separating between plates. So if in this case the dielectric is introduced, it doesn't affect D. So D is constant.
Oh yes, yeah. D is constant. V and voltage. I was saying the electric field will change also.
Wonderful. The electric field will change. So how many quantities are changing there? Four. Four quantities are changing, and that four is also here, which is the quantities that are identified except for Q. So the rest of the quantities except for Q should change. Okay. This is our next question. Question number 23. So let me check, guys. In case if you wish to write something on the chat, you can feel free. It's you are still for those that prefer writing. The chat section, we can still see your comments, be they answers or questions. We'll address them from the chat section. But anyway, question number 23 goes: a capacitor is constructed from two square metallic plates of sides L and separation D. Charges positive Q and negative Q are placed on the plates, and the power supply is then removed. A material of dielectric constant K is inserted at distance x into the capacitor as shown in the figure. Assume D is much smaller than x. What is the equivalent capacitance of the device? So there is the diagram. You have your parallel plates initially connected to a supply, then isolated or disconnected from the supply. The supply is then removed. That's the isolation. And then a material with dielectric constant, this yellow material is now placed in there. A distance x into the capacitor as shown. So if D is much smaller than x, which is the distance of separation is much smaller than the amount of the dielectric that has been inserted into the capacitor, what is the equivalent capacitance of this device? Where do we start? Or what do you think we do with the equivalent capacitance in this case?
And, I've okay. So if you look at this diagram, is it possible to calculate the region where it has a dielectric and the other region that doesn't have a dielectric and add the capacitance?
Okay. I think that would be proper. Why would we add the capacitance?
Will not be different. Wait, but will not. I think it will be different because this side has a dielectric and this side doesn't. So it will be affected differently.
Okay, good. So how do we add? Do we add them like capacitors in parallel or capacitors in series?
I don't know, sir. I don't know, sir.
What's your guess? Looking at the direction in which you apply your charge, those would appear to be what, series or parallel? The way in which
I can say series.
you would say
Series. I'm sorry, parallel.
Parallel, good, yeah. So it should be parallel
This
because
is
it would be series if we would have the two capacitance or the differences being in the line across the fields. So in this case, it's just two separate fields. It's like you have your capacitor like that, and then you would have the separation of the capacitances that's this way, which is different from having the same capacitor like this and then separating maybe the dielectrics like that. So in this case, you have your C1, C2. Here you have your C1, C2. So this comes in as a parallel, kind of a parallel equivalent to a parallel setup. This is equivalent to a series setup. Okay, so if we can add them like that, let's find those areas. We have said the equivalence capacitance, C equivalent, is equal to C1 plus C2, where C1 is, we have A1 E naught times K over D plus C2 is A2 E naught, there is no K there, over D. So the A1, what is A1? What is the area of the plates covering the dielectric?
We've been given, we know that their full length is, they just given us L, but also we know that length X covers the area, some area in the capacity.
Right.
So maybe we can, oh, length L is the length of the plates, or I didn't see that.
Length
Maybe
length L is the length of the plates, but it's both length and width, because we are told that this is like a square plate. So it has L on one side and L on the other side that we are facing right now. Two square metallic plates. So it's a square. So it's L by L for the whole surface area of the plate. So now the covered area is what we are asking. What is the covered area?
L minus, which one, for the one with the dielectric, or the other side with
the one with the dielectric?
Oh, okay, the one with the dielectric. Oh, yo, I don't know, sir, and I can't say X because
X.
okay, it's X, man.
So we say L times X, right?
Yes,
L times X,
L
so
times
the area
X
with E naught and a K there over D, plus the other one is L minus X. Do we agree?
L minus X.
Multiplied
Yes,
by
sir, L minus X
times E naught over D. So if we factor, we've got L E naught over D being common. And what do we have in brackets? XK plus L minus X. So that's L E naught over D plus, in brackets, L plus X K minus 1. That should be the expression you see in, do you see anything similar there? No. Okay, there. E naught L over D with L plus X times K minus 1. So this is our the correct answer. So that's the expression for the capacitance, equivalent capacitance of this setup. Then question 24 is one that's almost similar. A parallel plate capacitor with area A is made of two dielectric blocks in series. One of the block has thickness D1 and the dielectric constant K1, and the other has thickness D2 and dielectric constant K2, as shown in the figure. So there is the figure, the diagram. So D1 thickness K1, D2 thickness thickness D2 with dielectric constant K2. The arrangement can be thought as a dielectric slab of thickness D equals to D1 plus D2. What is the equivalent capacitance of the system? Assume the thickness D is far much smaller than the length of the plate. So can we get an expression for the equivalent capacitance of this system? Equivalent capacitance of this system.
So I don't think I understand the question. I didn't read well.
Okay, so
can you scroll up?
We have this parallel plate capacitor with area A. A is already given as the area. It has two dielectric blocks, the ones that you saw, one in blue and the other one is in orange, and they are arranged in series. Then the one block has thickness D1, its dielectric constant being K1. The other, the thickness is D2 with the dielectric constant K2. So that's what is shown here. D1, K1, D2, K2, and cross-sectional area A. So the question is, what is the equivalent capacitance of this system? What is the equivalent capacitance of this system? Do you understand it now?
No, sir. This one you will have to do it. This one I'm just lost, man. I don't understand it. Well,
so you see the question that you see this what I drew here. Do you see the my screen? What I drew on the screen? With the two capacitors. Yes, the diagrams that I drew and shaded showing parallel and series connections.
Your screen is kind of okay. I can see that. I can see them.
You can see them, right? Okay, so on those two diagrams, yeah, remember what we did with the first one where the dielectric is introduced from the side. By introducing the dielectric from the side, we said this ultimately becomes a parallel connection because from looking at the arrangement itself, the two different capacitors are parallel to each other and to the flow of charge or to the field that is created within the capacitor. Whereas in this case, the new arrangement that we have now is this one where the two dielectrics are in series. So they lie in series, making like a series capacitance connected in the a circuit like that. So which means still what you need to do to find the equivalence is just to think of the combination as a series combination of capacitors. So you have C1 with the dielectric K1 and dielectric K2 like that. So that makes a series arrangement. That's the only difference with what we did in the previous.
Okay, so I'm good so far.
Okay, good. So what that means is with the given information, we need to find the equivalent capacitance, and so that equivalent capacitance, C equivalent, is equal to, we'll still call it C1 plus C2. It's actually 1 over C1 plus 1 over C2 anyway. 1 over C1 plus 1 over C2, everything to the minus 1. So if we only have such two capacitors, this is product over sum. So we can do product over sum, which is C1, C2 over C1 plus C2. But the question is, what is C1? It is A1, E. Anyway, A is the same, so I'll remove the subscript. E naught K1 over G. And C2 is the same A, E naught K2 over D. So what is separate over D1 and over D2? So what is only distinguishing between the two capacitances of the dielectrics and the distance of separation or the thicknesses of the dielectrics. So with C1 and C2 having those values, we then substitute them into this expression. So with C1 being A E naught K1 over D1 multiplied by A E naught K2 over D2, everything over A E naught K1 over D1 plus A E naught K2 over D2. So now you need to reduce this expression to its simplest form. Can you try that? Tell me what you get. Can you try take a shot at that?
Okay, sir.
Tell me what you got.
I said it's too long.
Is
Can
it too
you?
long?
Yes.
I think there are very simple things to just cancel out from there. I thought it was now a matter of just cancelling out similar terms.
Yeah, I'm considering out, but it seems too long.
What's your expression? What expression did you get from your operations?
My operation is very messy. I give up.
How can you give up so fast? Okay, so the simplest thing is to identify the similar terms. A E naught, A E naught, A E naught, and A E naught are common in all of them, right? So we can factor factor out A E naught here with A E naught squared multiplying K1 over D1, which also multiplies K2 over D2. Do you agree about the top part?
Yes, sir.
All right, good. Then we have got also A E naught at the bottom, multiplying K1 over D1 plus K2 over D2. So the A E naught can cancel out the other one at the top. Our expression remains as A E naught multiplied by K1 K2 over D1 D2, everything over. We can put this under one denominator, which is if we use D1 D2, as a common denominator, we've got K1 D2 plus K2 D1, everything over D1 D2, right? So if the top part is over D1 D2, the bottom part over D1 D2, the D1 D2 can easily be cancelled out as well, leaving us with an expression AE naught K1 K2 over K1 D2 plus K2 D1. This is the simplest expression. That is the simplest expression. So that part would mean we should have one of the answers with this. So do we have a similar answer here?
Yeah, so I just understood how you took out the common facts and then cancelled out, then simplified it. I don't know what I was doing. I just
You gave up. Why do you give up? You just saw a lot of K1, K2, and all these letters, and so this is now an ugly expression, eh?
they were traumatizing.
No, don't give up easily. It's always as simple as it can get. So you should not think too hard or see it difficult. You should actually see it as an exercise just for your brain, eh? But anyway, which one is our answer from the choices given there? Which one would be the best choice?
I think is it C? C is our best choice.
C AE not K1 K2 with D2 K1 plus D2 K1. Okay, so there's something wrong with D2. It should be D2 K1 plus D1 K2. So there's none of these are giving those that choice. But it should be D1 K2 anyway. I know this one will say it's correct, but it should be D1 K2. It should be D1 K2. So take note, still there's a typo on that C. It should be plus D1 K2. So that's the closest anyway, because the rest are generally far from what we got. So that part should be D1 K2. Okay, then our next question is number 25. Number 25 goes, a capacitor C1 is connected to a battery charged to a potential V, and then disconnected from the battery, after which a second capacitor C2 is connected in series as shown to the first capacitor. What is the final potential difference across C2? So the capacitors. So we have three diagrams. So the initial state, the capacitor C1 connected to a battery, it gains a charge Q. Then after that, it is disconnected from the battery. The capacitor remains with this charge Q, and then it is connected to a second capacitor C2. The question is, what is the final potential difference across C2 after connecting like this? So what do we do with this question? What do we do with this question?
So can you go back to the question?
Okay.
I didn't
You
get
didn't
to read it.
get to read it. Okay, you can read through it. You can read through it.
Yeah. Yes, yeah. Can you go to the diagrams now?
Okay, so that's your first diagram for the charging circuit. Then after that, it's isolation and reconnection to C2. And what we want to find is the voltage across C2, V2.
Yeah. So I'm also not getting it. Can you solve it and see how and see your thinking process through this?
Okay, so the first thing to do there is remember the connection there for the two capacitors. The two capacitors after isolation are connected in what is this, series or parallel? They are connected in series, right?
Which one?
These two, the two
Yes.
capacitors are in series. So if they are connected in series, so what comes to mind? What quickly comes to mind?
That the voltage will be divided.
Yes, the voltage will be divided. And what about the charge?
The charge will stay
The charge should
the charge will stay the same.
the charge should stay the same. So the charge in this case for the combination, the charge Q should be equal to the total capacitance times the total voltage. We agree on this one, right? Because capacitance is charge per unit voltage. So our charge, which will be the same, will be equal to what we get from the total capacitance plus what we get for the total, what do you call this? For the total voltage. Is that so?
Your screen is kind of frozen now.
Let
I
me.
can't. I
Okay.
see. I don't see what you wrote.
Something happened. All right. Thank you for that. Let's see. Okay. There we are. So we're starting from here. So we're looking at the charge in the system after giving the capacitor C1 a charge Q. This will still be the charge that will be in the system after we connect capacitor C2. We have agreed on this, right? And
Yeah. Yes.
this total charge will be equal to the total capacitance multiplied by the total voltage. So what is the total capacitance for capacitors that are in series? It is product over sum C1, C2 over C1 plus C2, right? That's our total capacitance. And then we want to find V2, which should be equal to Q charge over C2. Do you see some clue there? V2 is the charge stored in C2 over the capacitance of C2, right?
Yes, sir.
Okay.
It,
So if we were to substitute, in this case, we substitute and replace for the Q with CT times VT. VT is basically V1 plus V2 in this case. So we can say VT equals to V1 plus V2. So we can now have an expression for our capacitance. First substitute for Q, it's CT times VT over C2. Then for our CT, we substitute for CT with this expression, which is C1, C2 over C1 plus C2, multiplied by VT, which is V1 plus V2, everything over C2. So we have taken this to be CT. This is CT according to that, so that's CT. And this is VT. And that's your over C2 like that. So what next? We can re-express this. C2 is common. Then we have got C1 over C1 plus C2 multiplied by V1 plus V2. The total voltage. So with this total voltage, V1 plus V2, this total voltage can be simply be expressed, we can simply express it as V. So we can simply represent this as the initial voltage, total voltage V. So we have V2 in terms of the total voltage V that is given in this case in the question. So that part, we have V times C1 over C1 plus C2, which is basically that choice there. So the same principle where we said we need to first find the total, to know that the total charge in the system doesn't change, but also express our total capacitance considering the capacitors that are in series. It gives us an expression for the total capacitance in terms of C1 and C2. Then knowing our total voltage, which is V, we can simply express V2 as the total charge, which is Q, divided by C2, and that gives us that expression. So I'm sure that should be quite straight. Any question?
No, sir, nothing from me.
Okay. So question 26 is a more or less similar question, which reads, a capacitor having a C1 is connected to a battery until charged. So it's a capacitance having capacitance C1 is connected to a battery until charged, then disconnected from the battery. A second capacitor C2 is connected in parallel to the first capacitor. Which statements below are true? So same scenario, capacitor connected to a supply, gains charge Q, then is isolated from the battery and now connected in parallel to another capacitor C2. So which statements are true? So they are the statements to consider for this new connection. Which of those statements are true? So if you find one that's true, you can indicate. Just tell me which one you think is true, and it would be nice to even explain why you think it's true. Which ones?
I'll say the first one. One
is true.
Is true. Yes.
Okay, so you have chosen one to be true. Do you want to explain why you think it's true?
Because now our in parallel, so in a parallel connection, the charge the charge doesn't stay the same. Is voltage that will stay the same, and the charge will be divided. And for the fact that it decreases, I don't know how to explain that.
Okay, so you're saying the charge on C1 would decrease because it will, anyway, it's a parallel connection. So it when the current flows to charge the other capacitor, the charge on it is different and hence would decrease to charge capacitor C2. So remember, we have in a parallel circuit or parallel connection, you have a branching of current, meaning the charge will actually redistribute into two branches. So the current that flows in either part of the circuit is not the same. It's going to be different flows that are actually causing different charges on either path. So it's unlike a series connection whereby the same current is generally the same charge flowing past every capacitor within the same line. So you would have the same charge ideally in each capacitor, and that same charge is the equivalent to the total charge in the system. So the charge in C1 will decrease. Charge in C1 will decrease, that's true. What
Okay,
next?
sir.
What else can we say?
Oh, I was saying I understand that. Thank you.
All right, perfect. Thank you for the that confirmation. What else? Which other statement is true here? Which other statement is true? Which other statement is true? Between 2, 3, and 4, are there still any true statements?
I don't think there are any truth. I think the rest of the statements are false.
Okay, so wait, let's see. The total charge on C1 and C2 is the same as the original. So if we add the charge on C1 and the charge on C2, will it be the same as the initial charge Q?
No.
Where is the other charge going to?
Oh, wait. Oh, the total charge for C1 and 2. Okay, yeah, yes. It will be the same because that charge is distributed between 1 and 2.
Yes,
And when you add it up, you get the equivalent.
that's
Okay,
right.
yeah, number 2 is true. I don't know why I overlooked it.
That statement is actually quite tricky. I think the phrasing of it also I don't like it as well. Total charge on C1 and C2, but I mean it is what it is. I think it's more of understanding the language than anything. Total charge on C1 and C2 is the same as, so it's like it sounds as if it's saying the total charge on C1 and the total charge on C2 is the same as the original, as if you are looking at them independently. Whereas it actually means that the total charge
Yes.
for both C1 and C2, I think it should have really like phrased it clearly to say the total charge for both C1 and C2. Adding C1 and C2 is the same as the original. That one will be quite clear, not a sort of vague. Okay, so we'll take that one too. We'll take 2. The total charge for both C1 and C2 is the same as the original Q. And any other true statement?
Four is definitely false.
For the
It
potential
cannot be.
difference across C1 decreases. Uh, the total potential difference across C1 will it be the same? It will be the same after pushing the charge. Remember, you are actually taking at least some part of the voltage from C1 to charge C2. But at the end of the day, the potential difference across both of them should be the same. So are you saying the potential difference across?
Also,
Yes.
well, when you're going to add capacitor C2, adding it in parallel, the before that voltage is the same. The voltage on C1 will decrease first.
Yes, 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 because it is now
Okay.
behaving
Okay.
as the source of driving the charge to C2.
Okay. So
You
I
see that?
understand.
Yeah,
Okay.
so four should be correct. What about 3? What about 3? What can we say about the energy? The total energy in both capacitors is the same as the original energy stored in C1. This meaning the sum in this case, total energy is sum in both. You see now they're saying the total energy stored in both. That both should have appeared also in 2. But anyway, total energy stored in both capacitors, is it the same as the original energy which was stored in C1? Do you think the sum of U1 plus U2 equals to the initial U?
Yes. Yes. I think it. Yes. It is the same.
Right, remember when you store your energy like from a certain source, let me say if the energy from a battery, right, is how do we calculate energy, by the way? It's VIT. So VIT is actually Q times T anyway. So QT can be the energy from the source, right? But now I'm saying QT, QV, sorry. So it's VIT, then I is Q over T, then you remain with QV, QV. So that QV is the energy from the source. So you've got your source giving off energy, which is Q times V. The energy that goes to the capacitor, E, why am I using, should I use? Okay, let me call it U source and U capacitor. U capacitor. U at the capacitor is half QV, right? So what is happening here is the energy that is basically coming from the source, half of it is used as to store the energy in the capacitor. Remember, some energy is lost in the process whenever these processes or these systems are happening because of the efficiency or inefficiency thereof. So now half QV means we're simply using half of the energy that came from the battery to drive the electrons or charges through, right? So that's how we have half QV. It is basically an average energy, right? Then when we do the same with the capacitor, if initially we have an energy U from capacitor U1 from capacitor C1, then the energy that will be stored in the two capacitors will be less UC1 final plus UC2 final, right? So at the end, the sum of the energies there, they are actually less than the energy that was stored in the capacitor before, because each is storing almost an equivalence of half QV and half Q times its equivalent phi. But that energy is basically because of our efficiency principles, that energy is less than the one from the source. So the total energy in both capacitors is less actually than the original energy stored in C1. So our true choices are only 1, 2, and 4. We have 1, 2, and 4 as true choices. Where's one? None of the statements 1, 2, 3, 1, 2, 4. There's 1, 2, 4, 3. Only 3 is true. All of the statements are true. So it should be 1, 2, and 4. Okay. Then the next question is number 27. A 15 microfarad capacitor. So a 15 microfarad capacitor is charged to 40 volts and then connected across an initially uncharged 25 microfarad capacitor. What is the final potential difference across the 25 microfarad capacitor?
Why don't they tell us how they are connected, or it doesn't matter?
It does matter. You see this part. Do you see how they are connected?
You just say connected across.
What does across mean?
Ah,
Tell me.
there's no across. It's just series of parallel. This one doesn't exist. Connected across.
What does across mean? Can across be series?
Connected across series. It doesn't feel right.
It doesn't feel right. It's not across is not series. So across should be
Sure, should be parallel.
parallel.
Yeah.
It's on the other side, opposite. Yeah, opposite and initially uncharged 25. So we have got a 40 connected across an initially uncharged 25 microfarad capacitor. This is the 40. So the voltage 40 volts, initially given 40 volts there if it's charged fully. So what is the final potential difference across V2? We want V2. So we've done an expression for a series connection. And what will we do to find V2 from a parallel connection?
You first have to find the total charge. We know that the charge will be the same. So you add the capacitor for C1 and C2. You find the total charge. Then using the charge, you can let me just solve it because I just lost my thought there.
Okay, but you're on track. Okay, try to solve it. Let's see. Can you try to solve it here? Your explanation is correct. You need to find initially your charge here, Q1, right? Which were not given, but you are given quantities that can enable you to do that. Then from there, you know that after the redistribution of charges, whatever remains Q1 final plus charge on Q2 should be equal to the Q1 that you found initially. But anyway, what you want to find is if you find Q2, if you can find this Q2, you can also find the voltage across the C2, the second capacitor. So you can try to do that. Let's see how far we get. The other guys, are you okay? Can you follow?
Yes, sir, we can follow.
Okay, perfect. So can we attempt to find that V2? Let's see what value for V2 we get.
Sir, I got 15 volts.
You got 15 volts.
Yes, sir.
Okay, can you take us through your steps? Let's see if we can follow.
Okay, I first calculated the equivalent capacitance.
Okay.
Then
C
then
equivalent.
I use that to find the.
And that was C1 plus C2.
I use that. Yes, sir.
C1 plus C2.
I used it.
And that gave you 40. Is that so?
Oh wait, I just realized I did a mistake at the beginning. I added the capacitance as 1/15. 1/C1 plus 1/C2. Ish.
How did you get the correct answer then? Okay.
Yeah, my answer is already wrong.
So 15
Just a
microfarads.
mistake.
Okay, let's see. So it's 15 microfarads plus 25 microfarads, right? Because these are in parallel.
Yes.
That should give us 40 microfarads. So that's the equivalent capacitance of 40. Right, with this equivalent capacitance, what would be the next step?
You find the total charge.
The total charge, and that total charge would be? How do we find the total charge?
I think it's going to be the charge which is equivalent, which is calculated, which is 40 and multiplied by the 40 volts.
Okay, so our total charge QT should be equal to the capacitance. Which capacitance do we use in this case? Times the, okay, so it should be capacitance times voltage. So we should find the initial charge that was there. That would be total charge should be equal to Q initial, which is what we see on the charge times voltage, which is C1 times its initial voltage. Is that what you mean?
Yes, sir.
Okay, so what is this C1? What is this C1? Which capacitor is this one?
It's 50.
15 microfarads
15.
multiplied by
Yes, sir.
which voltage?
The 40.
And what do we get for QT?
It's 600 microfarads.
600
Ah,
microcoulombs.
coulombs, yes, sir.
Yeah, you are now caught up in calling them farads like me. It's okay. Okay. So our charge is 600 microcoulombs. That's the total charge from the fully charged capacitor, and it will be the total charge after remember we talked of these conditions in one of the previous questions to say the charge on Q1 and plus the charge on Q2 will be the total charge in this system. So with this equivalent capacitance, we would then need to find the voltage across the equivalent capacitance. So the total charge being that and the equivalent capacitance. So the equivalent capacitance simply represents the two as a single capacitance. If we had only one capacitor there, it would be an equivalence of a 40 microfarad capacitor. And the charge within it will be 600 microcoulomb. What will be the voltage? What will be the voltage on that capacitor, which is voltage across? So that total voltage is Q over C. Am I right? That the total formula, the correct formula? Q?
Yes, sir. Q over C.
C equivalent, which is 600 microcoulombs over 40 microfarads. Okay, then this everything just gives us a volt. This 4 into 60 is 15 volts. So if this is the total voltage across the equivalent capacitance, what is V2? What is V2 then?
I think so. It's gonna be 40 minus 15. Is it minus? I'm not sure.
Not sure, not sure. Okay, remember. Okay, just hold on before you go. Remember what we've done here. This is a parallel connection. What is the first thing that you should remember about parallel connections? The voltage across a parallel connection or across parallel devices. What is the first thing that you should remember about a parallel connection? If you connect devices in parallel, be they capacitors, and even if they are different, but if they're in parallel, what is common between those capacitors? Or even for resistors, it will apply the same for resistors. If you have a 10 kilo ohm and 100 kilo ohm and they're in parallel, something will be common across them. What is that? What will be the same?
So can you repeat your question?
So my question is, in a parallel connection, what quantity remains the same for devices connected in parallel? Which quantity remains the same?
Oh, okay. The voltage will remain the same.
The voltage remains the same. So now what we have done is we have taken an equivalent capacitance of these two to be that purple capacitor there. So that's our C equivalent. And we find that the voltage across this C equivalent, point A and point B, the voltage there, VAB, is 15 volts, right? So it means this point is 15 volts, that point is 15 volts. If we, even if we remove the equivalent capacitance and we go back to the original capacitors C1 and C2, the potential at A and B have a difference of 15 volts, meaning we have 15 volts across C1. We put our voltmeter there. It measures 15 volts. We put our voltmeter here. It will measure what? Across C2, the voltmeter will also measure 15 volts. So 15 volts is just the potential across the equivalent capacitance. It therefore ultimately becomes the potential across V2 and the potential across V1 at the end. So for connections that are in parallel, the voltage is the same. That's where the whole point is. So once we find this VT, the potential across our equivalent capacitance, we already know automatically this is the potential across C2. This is our V2. Is that so?
Yes, sir, now I understand. Thank you.
Okay. So we should have 15 volts there. That's 15 volts. So I don't know, how did you get 15 volts after adding your capacitors as series capacitors? You actually made two errors that automatically countered each other, eh?
I don't know, sir.
Okay.
I don't know, sir. My steps are wrong, but answer correct.
The answer is correct, yes. That's why I was wondering if you added those capacitors wrongly. Otherwise, you actually did two wrongs that made it right. Okay, but anyway, find the equivalent capacitance between points A and B in the combination of capacitors with this Wheatstone on a Wheatstone bridge shown. So you have that Wheatstone bridge with A and B connected like that. We're now doing combinations of equivalent capacitance. So what will be the equivalent capacitance between points A and B in such a setup?
Oh, the question is asking for the total capacitance of this circuit. Or we could just add them by, let's just like first break down the circuit.
Okay.
And
So
say maybe
I'll start from
the ones that are in find the ones that are in parallel.
Is what I've done correct? So
Yes, sir.
we come from A, we go to one side of to the top, we connect to a 4 microfarad capacitor. We go to the bottom, we have a 2 microfarad capacitor. That part is okay. Then in between them joins the 2 parallel lines with an 8 microfarad capacitor. Is that so? Then we continue from the point where it joins. There is a 4 microfarad capacitor again and a 2 microfarad capacitor after it. Then we then connect to B like that. So with that arrangement, what would you say about our equivalent capacitance? So the first, yeah.
So far, most of our capacitors are connected in parallel. So you can add, yeah, you can add the ones 4, 4, 4, 2, and 2. Yeah, as parallel as a correct, sir.
You're saying we add which one and which one? You were breaking at some point, so I didn't hear some part of what you said.
Sorry, sir, I can't hear you. You're breaking again.
Yeah. So I'm saying you were also breaking. You said I should add which one and which one? Is it 4 and 4, 2 and 2, or which?
Yes, sir.
So 4 and 4, do we consider them in series or in
I'm
parallel?
saying.
So if you look at okay, I think the network should be misbehaving as of now. But anyway, besides, when you look at this Wheatstone bridge, we have been told it's a Wheatstone bridge. You actually see the way in which it makes a potential divider circuit. So in a potential divider circuit, you would know that if you have even your capacity, the potential across A and B, so the potential across the top arm is the same as the potential across the bottom arm. That's number one, because they are parallel lines. Then, because they are parallel lines and they are of equal magnitude, the capacitors at the top arm are equal magnitude, 4 microfarads and 4 microfarads, and the ones below 2 microfarads and 2 microfarads. It means the potential divides equally across them, such that if we have an initial voltage at A, we drop the same potential to that point X, and we drop the same potential to that point Y. So at the end of the day, Vxy is the potential difference between Vx minus Vy is equal to 0, because the two have the same, are coming after the same drops from potential at A. So when you drop like that, we then drop the rest of the potentials down that line. What does this effect mean? It means effectively the 8 microfarad capacitor has no effect. The 8 microfarad capacitor has ultimately no effect to the equivalence, to the capacitor equivalence of this system. It has no effect. So when we deal with the equivalent capacitance, then we are adding the two top capacitors as capacitors in series. So our C equivalent will be the product over sum of the top capacitors, so which is, let me give them names, C1, C2, C3, and C4. So C5 is out. So we've got product over sum of C1 and C2, C1 times C2 over C1 plus C2. So that's the total capacitance of that top arm added as 1 over C1 plus 1 over C2 and inverted. Then because the other arm is parallel, we do a simple addition. So the other arm contributes C3 times C4 over C3 plus C4. Excuse me. So once we do that, we can now substitute. Remember, I said the 8 microfarad the C5 does not count in this case because of the issue of the Wheatstone bridge and the potential divider arrangement that it makes. So C1 being 4, C2 being 4, we've got 16 over 4 plus 4, which is 16 over 8, plus 2 times 2, 4 over 2 plus 2, 4. So this will be 2 plus 1, which is 3 the microfarads. 3 microfarads is our equivalent capacitance. So we should have 3 among the choices given there. We should have that A as the correct answer. That's the 3 microfarads. Is it clear why we eliminated the 8 microfarads from the calculation?
Can you please repeat I want that part, the first part, with other substitution, the first part.
Okay, so we've said that in this kind of arrangement, this arrangement makes of this Wheatstone bridge makes what we call a potential divider. So in a potential divider, you would know that if you have 2 equivalent devices or along the same line, they divide the voltage equally between them. The voltage that across is divided equally between them. So assume we have 12 volts there and 0 volts at B. The potential difference or drop should be 12 volts across the top arm and bottom arm. 6 volt drop on 4 microfarad and 6 volt drop on the other 4. The same applies, 6 volt drop on the 2 microfarad and another 6 volt drop on the next other 2. So when we drop from 12 to and drop 6 to X, we remain with 6. And when we drop to Y, we remain with 6. The potential difference across X and Y is 6 minus 6. It's 0. There's no current flowing there. There's no charging of this capacitor. This capacitor effectively becomes ineffective. That's the first part of eliminating that capacitor. It becomes basically ineffective, so we can cut it out like that. So that is where I was saying Vxy, the potential drop across xy, because the potentials at x and at y are the same. Vx minus Vy is equal to 0. So when this one has no effect, now we're adding our capacitors. These are 2 capacitors in series. So for capacitors in series, we have 1 over C1 plus 1 over C2, which is equivalent to C1. Okay, so then this is inverted. Usually we take that and invert. So instead of getting that long way, we do product over sum, which is C1, C2 over C1 plus C2. So this is the sum of the capacitors at the top, series top. Then we have C1, C2 over C1 plus C2. And the capacitors at the bottom again do the same, C3 times C4 over C3 plus C4. So it is already the inverted total of the capacitors C1, C3 and C4 added together. So when we do that, because the two are also in, what do you call this? Because the two are also in parallel. When they're in parallel, then we simply add the equivalence of the top capacitor and the equivalence of the bottom capacitor like that. So this is equivalence C top. This is equivalence C bottom. So when we add, then we have, we are just substituted there to get 4 by 4, 4 times 4 divided by 4 plus 4. This is 16 over 8. 2 times 2 divided by 2 plus 2 is 4 over 4. That's how we got to 3.
Okay, sir. Thank you. Now I understand.
Okay, perfect. So that's how we get to the 3 microfarads for this type of question. Then here's another one. Consider the following capacitor circuit. What is the equivalent capacitance of this system? What is the equivalent capacitance of this system? So where do we start? Where do we start to simplify this problem? Where should we start? So there should be a part which is easier to eliminate. So we can eliminate that one first, then deal with the next part. So ideally, what would be your strategy? What approach would you use? Which one would you eliminate first? Or which part would you find the equivalent capacitance first?
Find the equivalent capacitance for the ones that are connected in parallel first.
For the ones that are connected in parallel first, yes. So like the 5 microfarad and the 4 microfarad, what would be the total capacitance there?
For the it will be 9, sir.
It will be 9. So we have got this part, 5 microfarad and 4 microfarad, giving us an equivalence of, let me use a different color, 9 microfarads. So we have an equivalence of 9 microfarads there. That part is eliminated. Where else do we go?
The ones that are connected in parallel, 2, 3, and 7 farads.
Yes, the 2, 3, and 7. So we have a 2, 3, and 7 here. So I'll put 2, 3, 7 and connect them like that. And what equivalence do they give?
Unifarads.
Come again.
It's 12.
12. Okay, so 2 microfarads with 3 microfarads and 7 microfarads. Their total there is generally an equivalence of 12 microfarads. So we have 12 microfarads from those. So we've reduced all these parallel parts to their equivalence. So it's now like we only have one capacitor there, which is an equivalent in a value of 9 microfarads, and we have only one capacitor again here, which has an equivalence of 12 microfarads, like that. So now what next? What will be the next thing to consider there?
Then you can add the ones that are connected in series, first.
Okay, so
Is the
at this point we've got these 2 arms, a series at the top and a series at the bottom. So the series at the top, the total capacitance CT, product over sum. What is the product? 9 microfarads multiplied by 3 microfarads divided by 9 microfarads plus 3 microfarads. Do you agree? Do you agree with me on that?
Can you repeat what you said?
For this line, so we've got this equivalence C, I'll call it, let me give it a new term maybe. So this is with C9 here and C3 here. The total capacitance there, CT, is C9 multiplied by C3 over C9 plus C3. So that's the 9 times 3 over 9 plus 3. So if you only have two capacitors in series, you can simply resort to this expression. It gives you the answer directly without the need to do 1 over C9 plus 1 over C3 and inverting. Remember? So this, let me just, this comes from CT is equal to 1 over C9 plus 1 over C3, and everything after we get it, we invert. So now if we choose C9 and C3 as our common denominator, then we have C3 plus C9 here as the numerator, but everything is to the minus 1. So if everything is to the minus 1, it means we are simply inverting this whole thing to get C9 times C3 over C9 plus C3. That's how we get this formula that we say it's the product of the two capacitors over their sum. It's product over sum. So if you have only two capacitors and they're in series, instead of doing 1 over C1 plus 1 over C2, you just do C1 times C2 over C1 plus C2. That's basically what we refer to as product over sum. So it gives you directly the answer without the need to invert. So that would mean when we have 9 and 3, that's 27 over 12 microfarads. That's our total capacitance at the top. Right, the total capacitance at the top. Then for the bottom series, what do we do for the bottom series? This is 6 micro. For these two at the bottom,
you do the same thing. You have 12 capacitor and another one connected in 6.
Okay, so it's
you can
C12,
just
yes.
Yeah, it's 6 multiplied by 12, then divide by 6 plus 12.
Yes, very good. You got it. You got it. So,
which it will give you 4.
So that's 12
yes.
by 6 over 12 plus 6, which is 72 over 18. It gives you 4, yeah. So that's 72 over 18. That gives you 4 microfarads. So that's the total capacitance at the bottom. Okay, so now we have got the total equivalent capacitance of the line at the bottom represented by the 4 microfarad, and the one at the top represented by 27 over 12. That's 2 and 1/4, 2.25. 2.25. So you have 2.25 microfarads. So with those two values, what do we do? Are they in series or they're in parallel?
They are in parallel.
They are in parallel. So what is our total equivalent capacitance if they're in parallel?
This one you can simply add them. I forgot the total. It's 4 plus.
Yes, 4 plus 2.25.
Yeah. Yes, sir.
4 2.25 at the top microfarads plus the one at the bottom 4 microfarads. That should give us 6.25 microfarads. Okay, do we have anything close to 6.25? It is the first one, nothing else close to it. Let's see if that's correct. So yeah, so we did everything right on that one. Well done, well done, well done. Okay, so I think, is it the last one? The last question for the day. Consider the same circuit you calculated the net capacitance above. So for this same circuit, now we are adding some more information. If a voltage of 48 volts is applied by the batteries, what is the charge on the 4 microcoulomb capacitor? The one shaded in red. If the battery supplies 48 volts, what will be the value of charge on the 4 microcoulomb capacitor? So if you have a 48 volt supply, what will be the value of the charge on the 4 microfarad capacitor? What's the first thing to do there? What is the first thing to do?
So where's the battery?
The battery is down
Oh,
there.
it's okay.
The battery is down there.
Okay.
It's that one. The one in green.
Okay, the voltage flowing through that bottom Y, it will also be it will also be flowing at the top Y.
Okay.
And but when it reaches the capacitor for 3 and the ones for 3 and 4, the ones that are in parallel, that is when the voltage will split there.
Okay. Yeah.
So, and can I ask, what are we calculating again?
We're calculating the charge on that capacitor. Charge on that capacitor.
Or the charge on the capacitor?
So ultimately, yes, we have to deal with the voltages so that we do capacitance charge in terms of capacitance and voltage.
Okay, and on the previous question, we've calculated the total capacitance.
Capacitance to be 6.25. We know the total. We know the total voltage. Yeah, we know the total voltage. So yeah.
And we can use that and the total charges.
And we can use the okay, so already we know that we have for the voltage across. So the voltage across. Let me make this diagram neat again. I'll remove this and that. Okay. Okay. Okay, so what we know, we have 48 volts. The 48 volts is across that point. We can call it AB. It is the same voltage across C and D. It is the same voltage across E and F. Do we agree? The voltage across A, B, C, and D is the same.
Yes, sir.
Good. So now remember we found the total capacitance, this one for the bottom line. So this whole bottom line, the total capacitance was 4. This whole top line, the total capacitance was 2.25. Remember? So we've got 48 volts across E and F. Let me put a voltmeter there. And that voltmeter would read 48 volts. But the total capacitance in this line is 2.25 microfarads. So what do you say, guys? What do you say?
I'm saying we can calculate the total charge.
Good. The total charge between which points?
Between E and F.
Between E and F. Good. How do we do that?
You will use the total capacitance for these two capacitors and multiplied by their total voltage.
Okay. All right. Good. So that means we have 2.25 microfarads multiplied by 48 volts. What do we get for the charge? What do we get for that charge?
You get 108.
108 microcoulombs.
Yes.
Okay. So this is the charge between E and F. So this is the total charge on this line EF, right? We agree? It is the total charge on the line EF. Is that true?
Yes, sir.
Then
Yes, sir.
it is also the charge. This is the same charge that is on this capacitor, the 3 microfarad capacitor. Do we agree?
Yes, sir.
And it is also the same charge that is on the equivalence capacitance of these two, which we said is 9 microfarad. So it is the same total charge QEF that we find on this equivalent capacitance.
Yeah.
QEF.
So you're saying, wait, we're saying for the 4 and 3 capacitor, right?
For the 4 and 5. 4 and 5.
For the which 5? Oh, it's 5, not 3. Oh, okay,
It's 5,
okay,
yeah,
okay.
so
Oh, yeah.
it's 5. So if for the 4 and 5, the total capacitance is 9 there, right?
Okay, yes, sir.
Because that total capacitance is 9 and the total charge is also equal to QEF on that 9, we can find the voltage on that total effective capacitance, right? Knowing that our voltage is Q over C. Voltage equals to Q over the capacitance. So knowing that the capacitance is 108 on this equivalent capacitance, everything, let me shed it. Yeah, blue would do. So there's a equivalent capacitance there that is represented by 9 microfarad, which has also a charge which is QEF. So it's 108 microcoulombs over the capacitance, which we're saying is 9 microfarads. It gives us the voltage across that parallel section. So what do we get from there?
12 volts.
12 volts. So the 12 volts is across this effective capacitance. So if we measure voltage from that point, and we have a voltmeter there, and it measures there, it measures 12 volts. And that's the 12 volts that's across. What's your conclusion?
The
conclusion,
4 and 5.
4 and 5 have the same voltage across them, so they all have 12 volts, right?
Yes.
So anyway, having found this as the charge on the effective capacitance. And we know that we have 12 volts across each and every one of these capacitors. We can now find the actual charge on the 4 microfarads capacitor. We know it has 12 volts across it, and its capacitance is 4 microfarads. What is the charge across it?
Yeah, the charge, you just multiply the 4 capacitance by the 12 voltage we acquired, which is 48
which is
microcoulombs.
48 microcoulombs. So of the 108 microcoulombs, the 48 is on this 4 microfarad capacitor. Then that means the 12 by 5 is 60. The other 60 is on the 5 microfarad capacitor. The total gives you 108. So you have 48 there, and we should see 48 somewhere. And that's correct. Okay, so I think that's about it, guys. Do you have any questions or something that needs clarification?
No, sir, I don't have any questions. I understood everything, sir. Thank you. Thank you very much, sir.
Thank you so much. Thank you for your participation. It was really awesome having you around.
Thank you, sir.
Okay,
Enjoyed the lesson very much.
Same to you. All the best with your studies. Goodbye for now. So that's all we had for you today, guys. See you in the next set of tutorials in the coming week. If there will be anything that you think we would need to have revisited, feel free to come through onto the platform, and we'll be able to readdress any queries that you have. Otherwise, from me and everyone at Yebo Physics, it's goodbye for now. All the best with your studies.